Hi, welcome back to Algorithms. So we're going to talk about some more DP concepts today, and in particular we're going to start to introduce the notion of a top-down DP algorithm in a little bit more rigor than we have before. So when we were talking about coin change, we observed this property of the optimal coin change problem that worked like this. Suppose I give you a pile of coins, right? So here's my pile of coins, and I say for the given set of denominations we're looking at, that's optimal change for something, right? So, and I say this is optimal change for, let's say, n. So if I say this is optimal change or minimal change for n, then we notice something interesting about the coin change problem, and that's that if I were to zoom in on one of these coins and pick a coin and pick it up and look at it, and it was a 4-cent piece. So suppose now this is a 4-cent piece. 4 cents piece. So if that's a 4-cent piece, so I pick it up and I remove it from that, and then I look at what's remaining, then this has to be optimal change for n minus 4. This is optimal. So let's make sure that all of our circles here are clear. So if this is optimal change for n, then the stuff I've circled in blue is optimal change for n minus 4. n minus 4. Okay. Because I know that it's optimal change, and I know that if I remove any coin from it, what's left has to be optimal change for something, and in particular, it's optimal change for n, what I started with, minus the value of the coin that I removed. Okay. And so it turns out we can use this concept to build a DP algorithm that actually can identify optimal change for any amount. And the way the algorithm works essentially does this. It says, let's make a list. Like let's say if we're looking for optimal change for n, let's initialize an array that has n elements in it, or I guess n plus 1 is the way we did it. And so our array, we'll call this array n. And let's see, for each change amount, we'll fill into the array the optimal number of coins that it takes to make change for that amount. So for I equals 0, it obviously takes 0 coins. For I equals 1, it takes 1 coin, and then so on. And so what we did is we thought about what it means to fill out this array. And so let's actually put some numbers in this array. 4, 5, and I'll just take it up to 6 for now. And so now what will sit in each of these spots in the array is the minimum number of coins it takes to make change for that value of I, using denominations 1, 3, and 4. And so I'm going to have my denominations be defined as 1, 3, and 4. Okay. So we said, okay, to make change for 1, it takes 1 coin. To make change for 2, it takes 2 coins. And the way we reasoned about that is we said, well, the only thing it could be, like the only coin that fits into 2 is 1. And so we know one of the coins has to be 1. So if you remove a 1, what's left over is 1, and we know how to make change for 1. Okay. So as I fill out this table, it's useful to think about which cells each cell is pointing to. So to compute optimal change for 2, what did we do? We said, well, optimal change for 2 contains optimal change for 1, right? So in some sense, all we need to know how to do optimal change for 2 is we need to know the optimal change for 1. So then for 3, we discovered that, well, look, there's a 3-cent coin, and so the best way to make change for 3 is with a 3-cent coin. And so the 3 place points at two different spots, and essentially compares 2 different spots. It compares the spot that we would be at if the optimal change for 3 had a 1-cent coin with the spot we would be at if the optimal change for 3 had a 0-cent coin. Right? So to understand how to make change for 3, we had to look at optimal change for 2 and optimal change for 0. And it turns out it's cheaper to make optimal change for 0, so that's where we go. Now the same thing happens for 4, except now we have 3 arrows that get drawn. So optimal change for 4, maybe the optimal change for 4 has a penny in it, has a 1-cent coin. If that's the case, then we're looking at this one. So it could be that it's optimal change for 3 plus a penny. Could also be that it's optimal change for 1. I'll do that just to keep this from getting too many cross lines. Could be optimal change for 1 plus a 3. Could also be optimal change for 0 plus a 4. And it turns out, of the 3 numbers that the 4 is pointing to, the smallest one is 0. So that's what is contained in optimal change for 4. All right, optimal change for 5, we get the same thing. So optimal change for 5 could include optimal change for 4. And I just messed up that. So that should be not 4 and 5, that should be 1. And then we're trying to identify optimal change for 5, so we'll leave that blank for now. So optimal change for 5, it could include optimal change for 4 plus a penny. It could also include optimal change for 2 plus a 3. And it could also include optimal change for 1 plus a 4. Right? Those are the 3 coins we could add to something to obtain optimal change for 5. And so, what are we doing? We're comparing 1, 2, and 1 when we're thinking about computing optimal change for 5. And the 1 is less than the 2, so either of those works just fine. And so what we know is that optimal change for 5 has 2 coins. Okay. And then we do the same thing for 6, and for 6 we say, well, it could include optimal change for 5, could also include optimal change for 3, and it could also include optimal change for 2. So it could be 2 plus 1, 1 plus 1, or 2 plus 1, and the smallest of these, of course, is 1 plus 1, and so we know that optimal change for 6 includes only 2 coins, right? And we know that it includes 2 coins because it is a 3-cent coin plus optimal change for 3. All right, so one thing that feels a little bit unsatisfying about this particular algorithmic approach is that we computed optimal change for every single possible value all the way up to 6. And we could ask, did we have to solve all those subproblems? Right? DP is all about identifying the subproblems that give you the solution to your problem, your overall problem, and then solving the right number of them, right? Solving as few of those subproblems as possible. And it feels a little bit like maybe we didn't need to do all this work. Like maybe we didn't need to solve all of these subproblems. And so one approach we could take is we could say, well, instead of solving every single subproblem, starting at 0 and working our way up, what if we started at 6? When we're sitting at 6, like we see where the arrows are pointing, we can identify which subproblems need to be solved to find the answer for 6. So why don't we start at 6 and then start solving the subproblems from there? And we will still be careful to keep track of the answers as we solve those subproblems. But instead of going and solving all of them, why don't we just solve the ones we need? So let's think a little bit about how that might speed up our algorithmic approach in some way. Maybe we could save some effort by not solving every single one of the subproblems.